Alrighty, let me introduce you to a concept called the total internal energy of a gas. This is what it is. Okay, we know that this gas is really just a bunch of little tiny particles, a lot of them, right? So we tend to think of air as just stuff, but really it's stuff made out of little particles that are moving randomly. Some are going slowly, some are going super fast, right? If you could imagine at one instant, if you could just freeze frame this and add up all the kinetic energy, that is, make a sum. That's supposed to be the summation thing, right? A sigma, right? If you were to add up all the kinetic energy, all the 1/2 mv squareds of all of those particles, that would be the internal energy. And we use the letter U for that. Okay, so what it is it's the number of particles that you've got times the average kinetic energy. And that's what that little bar is on that kinetic energy there, right? It's the number of particles. That's what that is, right? Okay. Multiplied by the average kinetic energy there. And this is a useful concept. Okay, it's one of the ways in a heat engine that the gas can actually store energy. Okay. Now this is Boltzmann's relation. Okay, this says that the average kinetic energy of a particle in a gas, okay, is 3/2 Boltzmann's constant, of course, right, times the absolute temperature. That's definitely kelvins. Okay. And the important thing here is to see that the average kinetic energy is directly proportional to the temperature. If you double the absolute temperature, you'll double the average kinetic energy. You'll also double the internal energy of the gas because we just multiply how many we have by that. Okay, that's the important thing, right? Is that the kinetic energy, oops, there's an I in there. Kinetic energy is proportional to the temperature. Okay. Now, notice also that Boltzmann's constant is also the same as the ideal gas, the gas constant divided by Avogadro's number. Okay. So if you divide 8.31 by this, you'll get this. You can try it right now if you're really bored, which you probably are. Okay. Now, what we're going to do is we're going to make a formula for U. In fact, I'm going to just hit the right arrow here. Okay. The internal energy then is the number of particles you have times this is the average kinetic energy of each particle, right? So if we just simply multiply that by this, we come up with this is the equation of the day, okay? With 3/2 nRT, right? Where this is the number of moles, right? Notice that the reason why that happens is that we get N over NA, right? So if you have the number of particles divided by Avogadro's number, you'll get the number of moles, right? That's the number of particles over the number of particles in a mole, right? Divided by the particles per mole, okay? You'll get the moles of a gas, right? So what's interesting here is a couple interesting things here, okay? One interesting thing is that notice that the internal energy is directly proportional to the temperature. The pressure and the volume don't matter in this case. If all we need to know is how many moles you've got, what the temperature it is, right? And you could have it compacted way down, you could have the volume quite large. As long as the temperature is a particular temperature and the moles are the particular number of moles, it's got the same internal energy, which is, I think, interesting, okay? The second thing that's interesting here is that this is good really only for monatomic gases, or really it's for ideal gases, okay? Okay, remember an ideal gas is just a point in space. The only way a point can manifest its energy is it moves, right? It has translational kinetic energy, okay? And the reason why there's a 3 there is because it actually has 3 degrees of freedom. It can go in the x direction, in the y direction, in the z direction, right? That's where the 3 comes from. If you have a diatomic molecule, right, this diatomic molecule, if you have, say, nitrogen or something like that, okay, this thing can actually rotate. That gives another degree of freedom, and I think it can spin the other way or something like that. And so I think that number changes, and it's been a long time since I studied that. But just understand that if you have something like nitrogen, this doesn't work. Okay, I think nitrogen stores a bit more energy at any particular temperature because it's got these other ways to store it, not just translational kinetic energy. And these are called degrees of freedom, and you'll learn that when you go to college from somebody who really understands it, I hope. All right, here we go. So let's use this for an example. Let's do an example problem here. Okay, the internal energy is 3/2 nRT. Okay, so here we go. What is the total internal energy of a balloon full of helium gas at standard temperature and pressure? Okay, so ultimately we want to do this. U is 3/2 nRT. Okay, standard temperature is 273.15. Okay, and we have the temperature, right? So that's going to be 3/2, and R is 8.31, right? And we have the temperature. The temperature is 273.15 kelvins. Oh, and this is joule per mole Kelvin. It fits in there perfectly. Okay, what we don't have is the moles, and of course we're going to have to figure that out from the volume and the pressure and the temperature. So let's do that. Let's use the ideal gas law. So PV is nRT, therefore N is PV over RT. There we go. Okay, so standard pressure is 1 atmosphere, so 1.013 E5 pascals. The volume is a sphere. It's a 12 centimeter radius sphere, so 4/3 pi times 0.12, 4/3 pi r cubed. So that's our volume, right? R is still 8, oh, that's meters, right? 8.31 joules per mole. One 5 kelvins. Let's see. This is intriguing. Okay, I'm looking at the units. The math here is not so hard. 1.013 E, whoops, E to the 5th times 4 divided by 3 times pi times 0.12 to the 3rd divided by 8.31 divided by 273.15. Oh, this is wonderful. Okay, so I'm getting that my number of moles is 0.323027, blah, 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 blah. Moles, so I'll plug that in. Okay. I'm looking at how we get moles. Oh, okay, I see. So pascals is newtons per square meter, cubic meter. So we get Newton meters up here, and that's a joule. And then we end up with, okay, I'm getting it. All right. So now let's look at this thing. Somehow we should get joules out of this, right? And we do, of course, because it's the moles cancel the moles, kelvins cancels kelvins. And the 8.31 joules per mole Kelvin, the units cancel out and we end up with joules. So let's try this. Let's go 3 divided by 2 times the answer I got on my calculator, which is this unrounded, right? Times 8.31 times 273.15. And I get 1099.8 joules. Now the hard part is to write that with 3 sig figs. Okay, so 1, 2, 3. I guess you have to go 1.10 times 10 to the 1, 2, 3 joules. There we go. Or just write it that way and just say, hey, only would round up, right? It'd be 1100, and then it'll have 2. All right, there you go. I do believe we've got that. Really a basic, simple idea, okay? The most important thing that you understand is that the internal energy, the total energy of the gas is proportional to the temperature, okay? If I double the temperature, I double the internal energy. If I triple the temperature, the kelvins we're talking about here, right? If I triple the Kelvin temperature, I triple the total internal energy. These things are tied. If the temperature does not change, okay, even if you change pressure and volume, if you do not change the temperature, you do not change the internal energy, okay? It's only moles and temperature, how much you have and what the temperature is, that totally dictates what the total internal energy is, okay? important concept.